In this video, we're going to take a look at three new properties and theorems that talk specifically about kites and rhombi. Remember the hierarchy we discussed last class. Um, it started with all quadrilaterals, and then from there flowed into two separate families, the kite family and the trapezoid family. Kites included rhombuses, or rhombi, and rhombi flowed into another shape, which was the most specific quadrilateral, or squares. The reflection symmetry of a kite is what we want to discuss now. So all symmetry lines of this kite, there is only one, and it goes through points A and C. And we call those points ends. So points A and C are the ends of the kite. And the kite symmetry theorem says that on the line containing the ends of a kite is the symmetry for that kite, the symmetry line for that kite. Symmetry lines cut shapes in half equally. So we know that angle BCA and angle DCA are congruent angles, and that angle BCD, the larger kite angle, was cut in half if AC, line AC, is a symmetry line. We also know that angle BAC is congruent to angle DAC as well, because again that symmetry line will slice the shape in half. What else do we know about this kite if line AC is a symmetry line? You might say that angle B is congruent to angle D, and that would be correct. You also might say that the diagonal connecting points B and D would be bisected as well. If these angles were bisected, then this segment would be bisected also. And what we're going to see in just a moment is that it is bisected specifically at a 90-degree angle. The kite diagonal theorem says the symmetry line of a kite is the perpendicular bisector of the other diagonal, and it bisects the two angles at the ends of the kite. So the kite symmetry theorem kind of told us the kite diagonal theorem. It sort of flowed out of that as a natural progression. Again, thinking back to the hierarchy, all rhombi are kites, but not all kites are rhombi. Because again, the items listed, the quadrilaterals listed in that hierarchy, everything above that shape applies to that shape as well. But the things that apply below do not necessarily apply above. So again, a rhombus is a kite, and both of those are quadrilaterals, being four-sided shapes. But just because it's a kite does not mean that it's a rhombus specifically. And we explored that last class in more detail, just as a review. And this, of course, again means that the theorems that we've just looked at apply to rhombi and squares as well. So how might the kite diagonal theorem change or be different from the rhombus diagonal theorem, which we're about to discuss? Remember, a kite has two sets of consecutive sides that are congruent, where a rhombus has the same, but what's unique to a rhombus is that all of the sides are congruent. Since all of the sides are congruent, the rhombus diagonal theorem will say that each diagonal of a rhombus is a symmetry line of the rhombus and the perpendicular bisector of that other diagonal. So the diagonals still meet at 90 degrees, but in this case both will bisect each other, and both are symmetry lines. Let's take a look at some examples where we will apply these theorems. Consider kite ABCD with ends A and C. Before I continue, remember I want to draw that picture. So here is a kite A, B, C, D, and I listed that specifically because it said the ends were A and C. So I can draw that symmetry line right now through A and C. And I know that these sides are congruent, BC and CD is congruent as well. Okay, I'll continue reading. If angle A measures 75 degrees, so this entire angle is going to be 75 degrees. Then what is the measure of angle ABD? ABD. So I need to cross the other diagonal right here, which I know is a perpendicular bisector, or was bisected by AC at a 90-degree angle. So the symmetry line AC was the perpendicular bisector to the diagonal BD. All of that information I know. And the angle I'm looking for is this angle right here. And so it might be helpful even to highlight. That's the angle we're looking for. Okay. The picture is drawn. The information that I know that was given is drawn on the picture. In a triangle, I know that the total angle measure is 180 degrees. 180 degrees minus the 75 degrees will give me 105 degrees left in this triangle ABD. So I'm going to cover up the piece of this kite that we're not discussing. With this blacked out square. So just this triangle now is what we're looking at. I know the angle ABD and angle ADB together equal 105 degrees. And since side AB was congruent to side AD, I'm looking at an isosceles triangle. So we could even just redraw. This is 75 degrees, angle A. Angle B now is what I'm looking for. And angle D, I know that these sides were congruent, so therefore these base angles are congruent. So I'll take the 105 degree sum of angle B and D, divide that by 2, and get 52.5 degrees for the measure of each of those angles. Now I can answer my question. The measure of angle ABD specific, this one that I highlighted originally, is 52.5 degrees. Example 2. Consider kite MNDP with ends N and P. So again, we should draw that kite. P, M, N, D. My symmetry line is showing the ends, tells me this side is congruent. These are congruent. Measure of angle M is 80 degrees. And the measure of angle NDM is 45 degrees. So I need to draw the other diagonal here. And this one here is 45 degrees. Then what is the measure of angle P? So we're looking for this entire angle here. Again, maybe let's highlight that. That's what we're looking for at the end of this question. And I might as well also highlight the question that matches, so we know exactly from the words and on our page what, on our picture, what we're trying to solve. The other information that we can place on this image is that this is a perpendicular bisector. PN was a perpendicular bisector of the diagonal MD. Alright, so we know a couple things about this picture. Because this kite was sliced in half along that symmetry line connecting the ends P and N, I know that angle M is congruent to angle D. Therefore, this missing piece, PDM, is going to be 80 degrees minus the known 45. $35 degrees. So this angle here, 35 degrees. Again, if I take the image and kind of cover the section that I'm not discussing and look just at the triangle PMD, I would see that angle D is 35 degrees, which we just figured out, and then angle M is 35 degrees because again we have an isosceles triangle and the base angles are congruent. The question asked us to find the measure of angle P. Well, 35 and 35 is a total of 70 degrees. And in the whole triangle there is 180 degrees. Minus the 70 degrees is going to be 110 degrees for the measure of angle P. Right there. Now that we've taken a look at a couple examples, I would consider pausing the video just now and try example 3. Once you think you have it, or if you get stuck, go ahead and hit play and see what see if you got it right. Let's put the information that I know on the picture as we go, since this time a picture was drawn. Ki, which is going to be equal to Ke, equals 2x squared plus 5x plus 17. Ke equals 3x squared plus 5x minus 47. IT equals 5z plus 7. And TE equals 13z minus 9. And TE and IT are also congruent sides. What is the possible length in units of each of the following sides? What is the possible length in units of each of the following sides? First, I would like to take a look at side IT, even though that's part B. Let's look at IT first. Since we've said in this kite that IT is congruent to TE, I will say that 5z plus 7 equals 13z minus 9. And we'll go ahead and solve for z. Subtracting 5z from both sides of the equal sign, and we'll add 9 to both sides of the equal sign, so that we have 8z on one side, all of our variables on the right, and the constants on the left, 16. At this point, solving to get the variable isolated, z equals 2. We have not answered the question though, because the question is asking what is a possible length of the sides. And all I have found is the value of z in this equation. So I need to take 2, the value of z, and substitute that in for either of those two expressions, but they ask for IT, so we might as well just use 5z plus 7. So the distance between I and t equals 5 times 2 plus 7, or 17 units. Now I'll take a look at segment KE. Again, KI and KE are congruent, so we will start by setting those equal to each other. 3x squared plus 5x minus 47 equals 2x squared plus 5x plus 17. I'm going to change colors just to keep things straight. We'll go ahead and solve this equation. Now this happens to be a quadratic equation, and so we want to move the variables and constants, everything to one side, and set the equation equal to 0, and let's see what happens. We'll subtract 2x squared from both sides of the equation. We'll subtract 5x from both sides of the equation. And at this point, you see that the x's cancel. So we were just going to have a squared variable term and a constant. So I'm going to change the plan a little bit, and I'm going to add 47 to both sides, and say then that x squared equals 64. Because I have x squared equal to this perfect square here, I can now take the square root of both sides, which is a nicer way of solving, is maybe faster. If the linear term 5x had stayed and there was some coefficient in front of the x term, all of the variables and the constants would need to be on one side of the equal sign, set equal to 0, and then you would factor or use the quadratic formula to solve and find the possible values of x. But again, since we have a nice perfect square, the linear term canceled, we can take the square root of both sides. So x is going to equal plus or minus 8. Remember, when you take the square root of both sides of an equation, you have to consider a positive and negative answer. Now that I have those answers, for x, the values that are possible for x, I will need to substitute those back into the expressions to find the segment KE. KE equals 3 times 8 squared plus 5 times 8 minus 47. 3 times 64 plus 40 minus 47 equals 192 minus 7, or 185 units. That is a possible value for KE, but KE could also be 3 times negative 8 squared plus 5 times negative 8 minus 47. And that would be 3 times 64 minus 40 minus 47, or 192 minus 87, which would be 105 units. Is also possible for the segment KE. What about segment IE? Oh, that wasn't the highlight tool. Here we go. Segment IE. What about that? Part C asks for segment IE. Do we have enough information at this point, given only the sides of the kite? No, we do not. The only thing we know is that this side is congruent to this piece because segment KT, that diagonal, bisects at a 90-degree angle the diagonal IE. So right now we do not have enough information. So now let's take a look at segment IE again, at that kind of question, but here we're given some different information. So IE will highlight in maroon and say that that whole segment, that whole diagonal, is equal to 2x plus 8. And we're going to say that this point in the middle, where the diagonals intersect, is point M. This side is congruent to this side, and they are 90-degree, and there's a 90-degree angle there. It's a perpendicular bisector. IM, that is this section, equals 2x plus 1. Find the distance, or the measure, the distance between point E and point M. Well, since that's congruent to IM, once we find x, we'll be able to substitute into this expression 2x plus 1, because both of those sides will equal 2x plus 1. By writing that on the picture, we see that 2x plus 1 times 2, or plus 2x plus 1, adding both pieces of the diagonal IE together, they will equal 2x plus 8. When we combine like terms in the left side of the equation, or distribute a 2 if you chose to multiply, you have 4x plus 2 equals 2x plus 8. And we'll solve this equation and have 2x equal to 6. So divide by 2, x equals 3. Again, we haven't solved or answered the question yet because they want us to find the distance between point E and M. So we'll take that x value of 3 and substitute it in for x into the expression and have 2 times 3 plus 1, or the distance between point E and M is 7 units. Example 5. Again, if you haven't been, this might be a good time to go ahead and pause the video, try example 5, and if you get stuck or believe you have the answer, go ahead and push play and see how you did. Rhombus RBUS, if the measure of angle R is 17.9 degrees, what is the measure of angle BUS? BUS, this angle right here. Well, we remember that in a rhombus, the diagonals are just like our symmetry lines. The diagonals are symmetry lines in a rhombus, and so they will cut the rhombus in half. They're just like the symmetry lines in a kite, where they would also be perpendicular bisectors of each other, the diagonals in a rhombus. So here we're just looking at segment BS as the symmetry line, which would mean that if angle R is 17.9 degrees, angle U is going to be the same, because this symmetry line cut the rhombus in half, and therefore angle BUS, its measure is also 17.9 degrees. The measure of angle USB is next. USB, so I'm looking for this angle here now. And it might be helpful to place the 17.9 degrees that we know in the picture. Okay, to find that angle, I know that in a rhombus all sides are equal. And therefore these base angles are congruent. They're also congruent to these base angles of this isosceles triangle because the sides were all the same in a rhombus, or because that diagonal bisected the ends of the kite, which could be S and B, or it could be R and U, as we look at this rhombus as a kite. Okay, total of 180 degrees in a triangle, and both of these base angles in the isosceles triangle would be the same. So first we'll subtract the 17.9 degrees that I know, which will be 162.1 degrees, and then we'll divide that sum of the base angles by 2 and get 81 5/100 degrees for all of these base angles. So the measure of USB being one of them equals 81 5/100 degrees. The measure of RBU now is looking for that entire angle, which would include 2 of the 81.5s. Where's the pen? Okay, so 81.05 degrees times 2 equals 162.1 degrees. And that math we didn't necessarily need to do right now because we already had that information when we divided that sum by 2 to get 81 and 5/100ths. We could have, instead of multiplying to get these two, recognized all four of these angles are the same, and therefore any two of them would equal the 162 and 1/10 degrees. Taking a look at this next example here, KITE is a kite. They've got some given information written on the page. And the first question is asking for the measure of angle ICT. This would be 90 degrees because the diagonals are perpendicular. Since the symmetry line, KT, is a perpendicular bisector of the diagonal IE. The next question asks for the measure of angle IKC. IKC, that's this angle right here. Well, in this triangle, I have 90 degrees, I have 58 degrees, and angle IKC, which would equal 180. Since we know one of the angles is 90, we know that the missing angle and 58 degrees are complements of each other. So we could say 90 minus 58 equals 32 and find that the measure of angle IKC is 32 degrees. The next question asks for the measure of angle TEC. TEC. So we're looking at this angle here. And we know that this angle is 72, and the angle TCE is 90 also. So again, same math as part B. We're going to see that angle 72 and the angle that I'm looking for are complements of each other. So 90 minus 72 equals 18 degrees. Next, they would like the measure of angle IKE. IKE. This time I will highlight. IKE, since this is a kite, and the diagonal TK is a symmetry line, I know that angle IKC and angle EKC are both congruent. So 32 plus 32, or 32 times 2, is going to equal 64 degrees. For the measure of angle IKE. The next question is now talking about side lengths and not the perimeter anymore. And so we'll take a look and see that side IT is 8 meters, which means that side TE is 8 meters as well. Side KE is 13.2 meters, and so side KI is 13.2 meters as well. We're going to add 13.2 plus 13.2 plus 8 plus 8 and get the perimeter of 42.4 meters. RHOM is a rhombus with RO equal to 3 centimeters. So this diagonal here is 3 centimeters. And I'll depict that in this picture by drawing the line RO here and saying 3 centimeters. And HM, the other diagonal, I'll depict that here. HM is 1.6 centimeters. Let's figure out some pieces. Okay, ZH. Well, we need to remember that in this rhombus, this is perpendicular bisector. Each of the diagonals are perpendicular bisectors of each other. So HZ is half of HM, and therefore 1 6/10 divided by 2 is going to be 8/10 centimeters. And ZO is half of the diagonal RO, and that would be 1 5/10 centimeters. The measure of angle HRM is this entire angle here, and they told us that angle HRZ, just half of it, is 21 degrees. So we're going to double the 21 degrees and get 42 degrees for the whole angle. And similarly, RHZ is now just one portion. It's not the whole angle, but just this little portion here. So we're going to take the fact that the measure of angle HRM is 21 degrees, and I'll redraw the triangle for us to see. RZ we know is 90. H we're trying to find, and R they told us was 21 degrees. So again, angle R in this diagram is a complement to angle H, so 90 minus the 21 degrees I know is 69 degrees for angle H, or angle RHZ in the larger picture. Hopefully going through these examples has been beneficial to you, that you found you were able to get a few of them correct before watching me go through them. And if not, and you got stuck, hopefully you now understand these questions and you see how the new theorems apply.